Reinforcement learning post-training updates every parameter in a large language model. Every layer, every head, millions of weights, all moving together. A team from Amazon and Minnesota asked a sharp question. Where, exactly, do those RL gains actually live? Are they smeared across the whole network or concentrated in a few layers? Their answer is surprising. Train a single transformer layer with RL, freeze everything else, and you can match what full parameter training achieves. Sometimes one layer even surpasses it. The setup is careful. 7 models across 2 families. Qwen 3 from 1.7 to 8 billion parameters trained with GRPO on math. Qwen 2.5 math with Dr. GRPO. Qwen 2.5 instruct with GGPO on agentic tasks. And DeepSeek distilled 7B on Skywork. 3 RL algorithms, 2 task domains. For every model they run standard GRPO backpropagation through the full network, but update the parameters of just one isolated layer, freezing all the others, including the embedding and the head. Then they scan. Layer by layer, across the whole stack. To compare layers fairly, they define one clean metric, the layer contribution, C of K. It normalizes the score of a single layer against the full RL gain. C of K equals the layer score minus the base model, divided by full training minus base. C of 1.0 means that layer alone recovers the entire RL gain. C above 1 means it surpasses full training. C near 0 means that layer barely matters. Run this for every layer and you get a contribution profile, a map of where RL learning actually concentrates in a transformer. Here's the machine. Equation 3. Standard GRPO, group normalized advantage, clip surrogate, KL penalty to a reference model. The gradient flows through the entire network as usual. The only change is which parameters move. Layer K is updated. Every other layer, the embedding, and the head is frozen solid. Equation 4 then scores it. C of K is the layer's held out score minus the base over full RL minus base. One layer trains. The whole network still does the forward and backward pass, but only that one layer actually learns. The profile is an arch. On Qwen 3 1.7b, the later layers contribute little. Layer 24 scores only 0.28. But the middle layers spike. Layer 10 reaches C of 1.14, surpassing full parameter RL. Layer 12 hits 1.12. RL gains concentrate in the middle of the stack, not at the edges. One middle layer can carry the entire gain, and it holds everywhere. Across all 7 models, the best single layer reaches C between 1.01 and 1.14. Math and agentic tasks. GRPO, Dr. GRPO, and GGPO. Middle layer concentration appears in every single model. The pattern even transfers across datasets. Spearman correlation 0.76 between 2 math sets. Wherever you train, the middle layers do the learning. One layer matching full RL 7 times out of 7. The picture. Before, every layer lights up during RL, full parameter training across the whole stack. After, just one layer in the middle carries the gain, the rest stay frozen, and the result is the same. 4 honest caveats. First, C of 1.14 is the smallest model only. On 4B and 8B, the best is 1.06 to 1.07, matching but not surpassing. Second, the layer scans are single evaluation runs, with no standard deviations. Third, there are no significance tests, so a C slightly above 1 could statistically overlap 1. Fourth, the guided training strategies that beat full RL, boosting or selecting the middle layers, are validated only on math, not on agentic tasks. The headline is real, but narrowly scoped. One layer, fully trained, can be enough. The practical payoff is bigger. Boost the best layers, or train only the middle few, and you can beat full parameter RL while updating far fewer weights. RL gains concentrate in the middle of a transformer. Find those layers, train them, and leave the rest frozen. Subscribe for the next paper breakdown.